Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 8, Section 4 on Formula Masses, Part 7. And so in Part 6, we talked about how to calculate empirical formulas. And the first thing you do is, if it's in a percent, make it into grams. And then we're going to do mass to mole conversions. Then we're going to circle the element with the smallest amount of moles. We're going to divide all the elements by that smallest number of moles to get ratios. We're going to adjust the ratios so they are whole numbers and in lowest terms. And if we need to, we can multiply all of our ratios by 2 to get a whole number. And we're going to write the empirical formula with the formula, and then the subscripts are those ratios we just found. And then you wrote down the problem. I found a jar labeled copper oxide. That's not so good. That's not enough information. Is it copper 1 or is it copper 2? Well, the first thing we're going to do is it in percents or is it in grams? It's in grams. So then the second thing we're going to do is we are going to convert them to moles. So let's do that. Okay, let's convert copper into moles first. So if you recall, what we do is, so I'll say it's copper. We take the mass, 2.96 grams over 1, and then we're going to take that, and we're going to put the molar mass of copper down here, which we find on the periodic table. So copper is 63.55. And then that is the mass of 1 mole of copper. And then we calculate that out. So 2.96 grams is 0. And we're going to do 4 sig figs. 0, 4, 6, 5, 7, 7. So 1, 2, 3, and then the 7, 7. So it would be 8 moles of copper. Okay, so we have 0.04658 moles of copper. And let's look at oxygen. We have 0.37 grams of oxygen over 1 times, well, 1 mole oxygen, and then we look up our molar mass of oxygen on the periodic table, and then we calculate the amount of moles. We get 0.023 125, so 13 moles oxygen. Okay, wonderful. What do we do with these numbers? Okay, step 2, mass to moles. Good. Step 3, circle the element with the smallest number of moles. 0.04, 0.02. That is this one. Divide all moles by the element with the smallest amount of moles. Okay, so we're going to have to do some writing here. So we're going to do copper first. Copper is equal to 0.04658 moles over the smallest number, 0.02313 moles equals 4,658 divided by 0.02313, and that equals 2.01, do 4 sig figs, 3, and it's a ratio. Our moles cancel, so it's a pure number. We don't need a unit. And then oxygen, yep, write this out. 0.2313 over 0.02313. Each of these are moles. Equals, well, that's going to be equal exactly 1. Okay, now let's see what we have to do. Adjust the ratio so they are whole numbers. Well, this is going to equal 1, and this is very close to 2. So 6, if needed, multiply all ratios by 2. Well, we don't because they were very close. And finally, write the empirical formula. So we know that this is copper. So we write our atomic symbol, and there's the ratio is 2 to 1. So we write 2, and then oxygen 1, but we don't have to write that. So Cu2O. Okay. So which one is that? Is that copper 1 or copper 2 oxides? Remember, the Roman numeral does not mean the number of atoms. It means the charge. So, which one is this? So, if this is -2, and there's 2 of them to make +2, that means each one has to be +1. So it has a charge of 1. So this is copper 1 oxide. Okay. Let's see. Did we answer the question? Is the copper 1 or copper 2 oxide? Yeah, we did. Good job. Okay, so let's talk about when empirical formulas are helpful. So, you don't need to write this down. When a new compound, such as a potential new pharmaceutical, is synthesized in a laboratory or isolated from a natural source, because we get a lot of drugs from plants, chemists determine its elemental composition, its empirical formula, and its structure to understand its properties. We focus on how to determine the empirical formula of a compound and then use it to determine the molecular formula if the molar mass of the compound is known. We synthesized a compound and analyzed it using mass spectrometry. So let's take a quick look at what that is. Mass spectrometry would give you a readout kind of like this. Okay, mass spectrometry is a fancy machine that gives you a mass to charge ratio of all of the parts, all of the elements in your compound. And it looks kind of like these. And you would get a readout that looks, there's another one, that looks kind of like that graph that we looked at. So here are some other pictures of mass spectrometers in labs. Here's a graph. So all types of labs would use them, like forensics labs, college labs, and medical labs. They would all use a mass spectrometer. Okay, looking here, this readout a mass spectrometer would give you, you can see this is our mass to charge ratio, which is characteristic of different elements, and you could look that up, and it tells you how abundant it is. So it tells you like, oh, there's a lot of carbon in this compound right here, and then like, oh, there's also a lot of hydrogen, and there is a lot of nitrogen as well too, and that's kind of what you could figure out with that. So we are going to find the empirical formula using the way we did before. So I'll get you started and then you're going to finish it. Okay, when we did mass spectrometry, we found the analysis shows a compound to contain 25.56% potassium, 35.41% chromium, and 38.03% oxygen. Find the empirical formula. Okay, here we go. So our first step is to, if it's in percents, turn them into grams. Okay, so let's do potassium first. Potassium is 26.56%, so we're going to change that into grams. Now let's just go ahead and do steps 1 and 2 together. So 2 says if elements are given in mass, convert each one to moles. So we'll just convert this into moles. So our molar mass for potassium, 1 mole potassium over 39.10. Okay, I think I'm going to set them all up and then we'll grab out the calculator. So then we have chromium, 35.41% over 1. Oops, forgot to do that part, not percent. We're supposed to turn the percent into grams. Times 1 mole chromium over, and chromium is 51.996. So that's going to be 52.00 grams. And then our last one is oxygen. So we have 38.03%, which would be grams over 1, and times that by 1 mole chromium, and oxygen, sorry, times that by 1 mole oxygen, over its molar mass, 16.00 grams. Now we grab out our calculator and do our calculations. So how many moles of potassium? And we're going to do 4 sig figs. 67928, so 3 moles. And then chromium, 35.41 divided by 52 equals 0.68096. So that's going to be 10 moles chromium, and 38.03 divided by 16 equals 2.3768. So 77 moles. Okay, wonderful. Okay, now we have found all the moles. And if you remember, our third step is circle the element with the smallest amount of moles and then divide all the moles by that number. Okay, so our smallest amount of moles is 0.6793 right here. So we're going to divide all 3 of our elements by that number. We'll start out with that one. Potassium equals 0.6793 moles over itself. Well, that one's going to be easy. And then chromium is 0.6810 moles over 0.6793 moles. And oxygen is going to be 2.377 moles over 0.6793 moles. Okay, this is where I'm going to leave you. I want you to do the calculations and then figure out how you're going to put it in ratios and then turn that into an empirical formula. And we'll talk about that in class. All right, thank you. Bye.